Hello everyone. So today we are going to cover one of the most important concept in the machine learning, that is the principal component analysis PCA. Okay. So now exactly what PCA is. In simple words, imagine you have a data set with hundreds of column, hundred of feature. Now that is too much to handle. So PCA helps you to shrink that down to just a few columns and few rows while making sure that you don't lose the important information. This technique is also called as the dimensional reduction technique. Now, here's really fun way to do this. Imagine you have a 3D sculpture and you want to take it into a photograph. You'll naturally choose the angle that shows the most detail, right? PCA does exactly the same. It finds the best angle to look at your data so that it captures the maximum information. Okay. Now, why should you even care about PCA? There are four big reasons. First one is the curse of dimensionality. When you have too many features, your data become very sparse and your model struggles. So PCA fixes it. Second, noise reduction. Some feature in your data are just noise, so they don't add any value to it. PCA automatically pushes those aside. Third is the visualization. You can compress your data down to 2D or 3D and actually see your data, spots, clusters, and find the outliners. Fourth one is the speed. Fewer features means your model can be trained faster. Okay, now this is the core idea behind this. PCA is all about finding the direction in your data where the variance is maximized, meaning where your data is mostly spread out. These directions are called as the principal component. The first principal component captures the most variance, and the second captures the next most, and so on. And each of them is perfectly perpendicular to each other. Now let me walk through the actual steps of PCA. First one is center your data. Subtract the mean from every feature of your data to balance it out to 0. Second, compute the covariance matrix. Tell this how your feature are being related to each other. Third, do the eigen decomposition. This sounds scary, but you have to find the special direction, the eigenvectors, and how important each direction is that you can find using the eigenvalues. Fourth one is pick the top components. Keep the direction with the highest eigenvalues, and that will be carrying the most information. Fifth part is project your data onto a selected component. Now you have the data live in much less space. Okay. One more quick notice that in scikit-learn you actually use something called as SVD, singular value decomposition, which we'll be covering in the upcoming lectures. So instead of computing the covariance matrix directly, this is more stable. Okay. Moving forward towards the next section, that how many component variants, secret plots, and the reconstruction part. Okay, so here we're gonna see that how PCA actually gonna work and how it actually gonna keep the data. This is a super important, because if you keep too few, you'll lose information, and if you keep too many, then you will not really compressing anything. So PCA gives you a very clear answer that via something called as explained variance. Every principal component explain a certain percentage of the total variance in your data. For example, the first component might explain 50%, the second might 25%, and the third might 12%, and so on. Okay, so the thumb rule is keep enough of the component together so that they can explain at least 95% of the total variance. So that's the sweet spot between the compression and the information retention. Okay. Now, do you know how you can visualize this out? You can visualize this out using a Scree Plot. It's just a bar chart where each bar showcases how much variance one component explain, and there are curves showing the cumulative total. Okay, you look for a elbow, the point the bar stop dropping sharply, and the elbow point is usually the cutoff or the threshold point here. Okay, for example, in our node, the first three components together explain about the 87% of the variance. That's very reasonable cutoff. Now you're gonna gone about maybe from 300 features to just 3 features. Okay. Now the next concept is reconstruction. Since PCA compress your data, now you have to get it originally to back. So the answer is yes, you can get it. You can reconstruct your original data from the compressed. It won't be 100% perfect, but it will be close enough. And the reconstruction error tell you that how much information is lost. Okay. So here are some of the direction trade-off given. Now let's have a quick comparison between PCA and the other popular technology that we have that we'll be talking about is the t-SNE and the autoencoder. So first of all, PCA is linear. It find out the straight line direction in your data set. It's faster, it's interpretable, and you can reverse it using PCA when you want to pre-process your data before feeding it into any machine learning model. Now the t-SNE is a non-linear part. It is great only for the visualization, making beautiful 2D plots of your data, but the key warning is that never use TCA as an input to your model. It only look out for feeding into the algorithms. Third part is the autoencoders. Autoencoders are the neural network based. They capture the very complex non-linear pattern, but they show more and more data. So the simple rule is that PCA first, then take it as your starting point. Okay. Moving forward to next section, we have the limitation, pro tips, and some of the key takeaway. Okay, so there are some of the limitation for this technique. Number one, PCA is linear. It can only find out the straight line patterns in your data. If your data has complex curve or non-linear structure, PCA will miss it out. In that case, you will use kernel PCA or the autoencoder instead. Number two, PCA is sensitive to scale. If one feature has a value in 1000 and another just has value from 0 to 1, PCA will think that the first feature is more important, but just because it is bigger in number, so that's wrong. You should must standardize your data before using it on a scale. Third is the Gaussian assumption. PCA work best when your data is roughly normally distributed. If your data is very skewed and has multiple clusters, then weird shapes, then PCA might not capture the real structure. Number four, it is hard to interpret. Each principal component is a mixture of all the original feature, so you just can't say PCA PC1 equals to age, PC2 equals to income. It combines of everything, which make it harder to explain to a non-technical person. Number five, outliner sensitivity. If your data is having extremely outliner and you have not made it using feature engineering and feature scaling, then this can mess it up because of the covariance matrix. Now here are some of the tips while using the PCA. So you can go through it. It's about that the 95% variance rule. It about that scale your data first, and whitening. The tip 3 is about whitening. After projecting your data, you divide by the square root of the eigenvalues. These gives every component equal variance, which is helpful before feeding the data into neural network or the KNN, K-mean clustering. Sorry, not KNN. Okay, then we have tips about the data set, massive data set, so how PCA help to compress it out and everything. Yeah, so here are some of the tips related to it given. So let's wrap up it about taking the complete takeaway of the PCA. So PCA finds the direction of the maximum variance. The eigenvalue of each component tell you how much variance each carry. PCA is linear and approximately invertible. Fourth point is that you need to always standardize it first. Fifth, that for a non-linear data, go for a kernel PCA or autoencoder. Sixth, that reconstruction error is sum of the eigenvalues you dropped out. So it exactly mean how much of the information you sacrificed for compression. Okay, so that's about everything about the PCA. Thank you so much.